Hello and welcome back. In the last session, we learned to design rock support using queue system. In this session, we will learn to design underground rock support using RMR. I hope you still remember well RMR, rock mass rating. That is another common rock mass quality classification system. As a quick reminder, the 5 parameters to calculate the basic RMR are shown here in the equation. RMR rating and rock mass quality classes are shown in the table. The last row suggests the average stand-up time and the span of tunnels and mines in rocks. RMR is a measure of rock mass quality, as well as a measure of rock stability in relation to opening size. RMR can be used for design and analysis of various rock engineering projects for both mining and civil engineering, including underground excavation of tunnels and mines, slopes and surface mines. You may remember we used RMR for slope stability analysis. As we have learned in the rock mechanics session, one of the advantages using RMR is that it has been coupled with unsupported span and stand-up time, as shown by the chart on the right. By using RMR, we will be able to estimate the stand-up time for a specific unsupported span in normal underground support installation. This is rather useful for planning the excavation cycle in terms of advanced length, stand-up time, and temporary support installation. What we usually have from site investigation and from geotechnical report are the basic RMR rating. Similar to what we have done for using RMR for slope analysis in session 2.5, we need to make adjustment of RMR for tunnel support design. In this case, RMR rating needs to be adjusted for tunnel alignment with respect to joint orientations. The adjusted RMR is simply the original RMR plus the adjustment. The condition for tunnel excavation with respect to joint orientation can range from very favorable to very unfavorable. The table below gives the adjustment for each of the conditions, ranging from 0 for very favorable condition to -12 for very unfavorable condition. Now let us examine what makes favorable and unfavorable conditions for tunneling in joint rock masses with respect to joint orientations. I think from those diagrams, you can appreciate easily the effects of joint orientation on tunnel excavation. We generally can expect a smooth excavation operation when drilling or excavating the rock along the joint dip, but less smooth when drilling and excavation is against joint dip. Particularly, the joint has low dip angle. Drilling may be deviated by the joint. Overbreak may happen by blasting and cutting. The most problematic concern is when joint strike is parallel to the tunnel alignment and with steep dip angle. Wedges and blocks are more likely to be formed on the tunnel roof continuously. In fact, in a later session, when we deal with design of cavern layout and orientation, we specifically highlighted to avoid joint and the line of joint section parallel to the tunnel and the cavern alignment. Now, by knowing how the tunnel alignment and advance is geometrically related to the joint orientation, we can make the adjustment to RMR. For rock support using RMR system, both the original basic RMR and the adjusted RMR must be used. The rock support design guide using the original RMR and the adjusted RMR are reproduced here. By knowing the original RMR and the adjusted RMR, we can identify the support type A, B, and C to J, K, and L. The RMR design guide is supported by the explanatory notes on support types, and they are showing on the next slides. Here are the explanations on those support types from A to L in the RMR support design guide. Each of the types from A to L are self-explanatory, so I will not explain one by one. Patterned bolts are in fact the same as systematic bolts, with different spacing. Bolts here are fully grouted. You may have noted the use of yielding steel arch when there is excessive stress changes. L type, being the worst case, is applied in very poor rock mass. The stand-up time is extremely short. Therefore, it is important to avoid failure development by installing support quickly and immediately after excavation. Hook and Brown made the supplementary notes to support design using RMR guide. The RMR rock support design guide uses the original and the adjusted RMR rate to obtain support requirements. Rock bolts are generally ineffective in highly jointed rock masses and should not be used as a sole support when joint spacing rating is less than 6 or average joint spacing is less than 0.1 meter. Support recommendations in the table are applicable to mine openings with stress level less than 30 megapascal. In fact, this may also be applicable to deep tunnels and caverns. Large chambers should only be excavated in rocks with a just total RMR of 50 or more. Otherwise, it would require extensive support and become non-economic. The explanatory and the supplementary notes did not mention bolt lengths. Recommendations on bolt lengths and spacing are summarized in the table here. The minimum bolt length is recommended to be the greatest of the following: twice the bolt spacing, or 3 times the average joint spacing for critical rock bolts, or 0.5 B for span less than 6 meters, and 0.25 B for span greater than 80 meters. The maximum bow length spacing is recommended to be 0.5 times the bow length or 1.5 times the average spacing of joint in the rocks. If wire mesh is to be anchored by the bolts, then a bolt spacing greater than 2 meters makes attachment of the mesh practically impossible. The RMR rock support guide indicates the thickness of shotcrete. However, shotcrete, particularly fiber-reinforced shotcrete, the thickness should not be exceeding 20 centimeters. Thick layers of shotcrete may be applied occasionally to a small area of particularly poor rocks. In addition, rock bolt design for major zones of instability, for example, seams, faults, and shear zones, should be subject to stability analysis. In general, systematic bolting with fiber-reinforced concrete should be used for permanent roof support that will be occupied by people or used as important facilities. We have mentioned earlier that RMR can be used to estimate unsupported span and the stand-up time. The estimation is done on this chart. Here, by knowing the RMR, we can estimate maximum unsupported span from stand-up time and vice versa. For example, given the RMR at 40, if the stand-up time allowed is 2 days, the estimated maximum unsupported span is 2 meters, as shown by the red arrows. Or, if the unsupported span is 4 meters, then the stand-up time is about 25 hours, shown in blue. Here is an example of using the RMR design guide to guide the excavation and the support of 10-meter span rock tunnels. It provides rather specific guides for rock excavation and rock support of each rock mass quality class. For example, for tunneling in good rock mass with RMR of 61 to 80, full-face excavation is suggested with 1 to 1.5 meter advance. Recommended roof support are systematic bolt with 3 meter in length and 2.5 meter spacing, and a 50 millimeter shotcrete, with occasionally wire mesh to be used. I want to give another example to use RMR for support design. It is the same example we have done in the last session using Q system. Again, it is a railway station cavern with span of 60 meters, wall height of 6 meters, in fair rock mass with RMR of 50. We need additional information on the two joint sets orientation with respect to tunnel access to calculate the adjusted RMR. Joint set 1 has a strike perpendicular to the tunnel access and dips at 30 degrees. Joint set 2 has a strike parallel to tunnel access and dips at 70 degrees. First, you need to work on adjustment for joint orientations. By checking each joint set, for joint set 1, if the excavation direction is against the joint set 1, the condition is unfavorable. If the excavation direction is with joint set 1, the condition is favorable. For joint set 2, the steep dip angle and the parallel to tunnel, the condition is become very unfavorable. Therefore, the overall condition is very unfavorable, and the adjustment is -12. The adjusted RMR is 50 minus 12 and is 38. With the original RMR of 50 and the adjusted RMR of 38, you can use the RMR rock support design guide to get the support requirements. It ends with support types C and D. Because it is a train station with a human occupancy, the roof should be shotcreted. Therefore, we will use roof support with support type D, which is patterned and fully grouted bolt at 1 meter spacing and with a shotcrete of 100 millimeter thick. The shotcrete should be steel fiber reinforced to provide additional safety for human occupancy. Bolt length is 0.25 to 0.3 times the span, which gives 4 to 5 meters. Perhaps you can compare the support design using RMR here with the support design using the Q system in the last session. RMR is a widely used empirical tool for rock engineering design. It is used for tunneling, slope engineering, and mining. We have learned RMR for slopes. Later, we will also learn RMR is used for caving mining. Using RMR to estimate stand-up time and the maximum unsupported span is particularly useful in underground excavation, particularly in relatively low-quality rock mass. It helps to determine the advancement of each round of excavation and the timing for support installation. The design is primarily for tunnels of small to medium size, mostly below 10 meter diameter. The design does not sufficiently address the size variation. The support requirements are rock mass quality dependent, but not size. Size effect is mentioned in stand-up time, but not in support design. Design does not consider the usage and the safety requirements. The only mention is the use of fiber reinforced shotcrete on roof support for human occupancy. This is the end of session on rock support design using RMR. Goodbye and see you later at the next session.